Hello. Hello and welcome. This is quite a complicated problem, the most general problem you can encounter in a gas turbine. Well, let's take a look at the schematic first. There are two compressors: multi-stage compression, multi-stage turbine, regeneration, reheat, intercooling, you name it. So to solve this problem, it's best to go to a simpler problem first. So what I'll do, I'll start from the test step page, and you know that we have to launch open specific gas power cycles PG model, and that brings up lots of hands-on examples. And this particular problem with this multi-stage compression builds upon this example, this particular example, example 5. So I urge you to go over this video first, and all we are going to do is to add this, split this compressor into two compressors. If you look at the circuits, two compressors, and put an intercooler in between. So let's pick up the test codes from here, and I'll just go over as we regenerate the solution, go over different steps in this problem. Control V and load. Okay, the solution has been regenerated. So let's start from the I/O panel, show the user codes only. Notice the total compression ratio is 12. The high pressure turbine has a compression ratio of 3. Therefore, the low pressure turbine and the low pressure compressor, P ratio LP compressor will be 4. Think about it. The compressor, the low pressure compressor goes from 1 to 3, and the low pressure turbine goes from 11 to 13. They must be matching, as opposed to compressor 2 and turbine 1. They will be matching in this problem. Okay, so the maximum temperature, the turbine inlet temperature, is given to us. Reheat temperature, the inlet temperature to the second turbine, compressor 1 and 2 efficiencies, turbine 1 and 2 efficiencies, and the efficiency of the regenerator, everything given. So in the state panel, is straightforward now. State 1 is the compressor inlet state, temperature and pressure given, and the volume flow rate is given. Of course, mass flow rate is going to be the same everywhere in this problem. For the second state, which is the isentropic exit state, the pressure is going to be P ratio of the low pressure compressor times P1, and of course entropies are equal. State 3 is the actual compressor exit state. Again, we can get that from P ratio, the pressure is the same, but the enthalpy is obtained from, keep an eye on this, keep an eye here as I move the pointer over enthalpy. You can see the formula that is used that includes the efficiency of compressor 1. From state 3 to 4, we have the intercooler, which is just a heat exchanger losing heat. Pressure doesn't change, so pressure is the same. Temperature at 4 is same as temperature, well, because we have cooled down the heat exchanger 3 to 4. At state 4, we have cooled the air down back to temperature 1. So the pressure doesn't change, so therefore state 4 is evaluated. Of course, then we send it to the next compressor. State 5 is the isentropic compressor exit. Pressure, you can see entropies are equal, and the pressure is obtained from the total pressure ratio this time, P1 times P ratio. That's the pressure at the exit of the second compressor, will be 1200 kPa. Okay, and state 6 is the actual exit condition of the compressor. State 6, again the pressure will be same as state 5, 1200 kPa, and again the compressor 2 efficiency is used to produce the enthalpy. Again, the compressors need not have the same efficiency. That's why we define variables in the I/O panel. Well, after that, After the second compressor, as you can see, the problem becomes same as before. After the second compressor, we go into the regenerator, and the rest of the problem is exactly identical to what we have done in the previous solution. So I'll just stop looking at all the other states. You can go to the graphics panel and realize that only thing we have done is split the compressor into two parts. So go to the device panel now and go over the devices that, device 1 is the compressor 1, device 2 is the intercooler, heat transfer is done here. Device 3 is the second compressor, against negative work, means it's consuming work. And the rest of the devices are just as before, except everything has been shifted. So device 9 is the last heat exchanger and getting us back to state 1, 14 to 1. So now that we have calculated all the devices, in the cycle panel, all the results are already compiled because the cycle is complete. Thermal efficiency has been found. Net work, which must be equal to net heat, are shown here. And you can easily conduct any desired parametric study following the same process, same procedure that we did in the last problem.